Okay, so yeah, welcome everyone to this third session of the Proof Complexity Workshop. Today we'll have two talks. So one is by Robere, continuing on the TFNP topic we had in the last session. So he'll be talking about proof circuits and communication. And then Jan Krajcek will be talking about proof search in the second part. So Robert is an assistant professor at McGill. He has a lot of work in some important work in proof complexity, a lot of it relating proof complexity to other areas, including circuit and communication. He has several papers on lifting and on TFNP. So so today he'll be talking to us about this. So please go ahead, Robert.
Yeah, all right. So thanks. So today I'm going to talk about some recent work connecting proof circuits and communication complexity, and in particular the theory of TFNP. So this is going to be closely related to Neil's talk and Sam's talk from yesterday, but kind of taken from a slightly different angle. So the starting point for Neil and Sam's talk, if you went to them yesterday, was more of a logical type setting, whereas the starting point for me is going to be lifting theorems, which probably a lot of people have at least heard of in this workshop before. So what's a lifting theorem? Well, there's been a recent explosion in results on these lifting theorems that connect query complexity of certain problems to communication complexity of certain problems. So just for a very sketchy description on what a lifting theorem is, at least in its most basic form, the idea is the following. So suppose we have a decision tree for some Boolean that solves some Boolean function f, so it computes it using some queries to the input variables of f. Then we can take f and we can replace every single input of f with some gadget function g on some new independent variables, say x and y, drawn from this set. And then after doing this composition, we get a natural two-party function, which is really naturally sits in the realm of communication complexity. And so we can ask, okay, what's the best communication communication protocol for solving this composed function? And it's not hard to sort of convince yourself that, if once I do this composition, one obvious way to compute this composed function is just to simulate the decision tree. So if the decision tree is going to query, some variable x, and then it gets 0 or 1, say, then Alice and Bob, well, Alice can just send, Alice and Bob can simulate this query by just evaluating, if x is the ith variable, Alice and Bob can just evaluate gxy. So maybe Alice sends all of her input xi to Bob, and then together they can evaluate the gadget and then continue on like that, right? So in this way, it's not hard to see that for these composed functions, the decision tree complexity is clearly like an upper bound on the communication complexity. However, a lifting theorem basically says that if the gadget g is chosen correctly, then this simple, obvious strategy is actually the best one. So you can't do any better than just simulating this naive strategy where you query all of these bits and just compute each g individually at each coordinate. Okay, and these results are really nice because, well, for two reasons, I think. So the first is that they let us lift decision tree lower bounds to communication lower bounds, and decision tree lower bounds are usually very easy, while communication lower bounds can be quite difficult. And the second reason is that it's very, very flexible. So I can start with kind of any function I want, or as we'll see, it doesn't even have to be a function. It could even be a search problem. And just by composing with this gadget g, I arrive at a hard function for communication complexity. So this gives a lot of flexibility when you're trying to construct hard functions for proving different kinds of lower bounds and upper bound results. Okay, so this workshop is about proof complexity. So I'm going to be interested kind of in how lifting theorems are related to proof complexity. And there's been a long line of of work in the past decade using lifting theorems to derive new lower bound results and upper bound results in both proof and circuit complexity. So this isn't even a complete list, but it's just to give you an idea of like the kind of advances that have been made ever since these theorems have taken sort of central stage. And the proofs of all of these results in proof complexity and circuit complexity, ultimately they place total search problems at the center. So in particular, in proof complexity, the important role it turns out to be played by a total search problem associated with refutation. So this is this false clause search problem. This was mentioned by Sam in his talk yesterday afternoon. And in circuit complexity, probably it's also familiar to you that this the central total search problem that sort of captures circuit complexity is this Karchmer-Wigderson game that was introduced by Karchmer and Wigderson. And to apply these lifting techniques in order to get interesting lower bounds and relationships between proof systems and circuit models, what we need are query models that capture proof systems on the one hand, and communication models that capture circuit classes on the other hand. Okay. And now, classically speaking, there were a few examples of this. So maybe some people are familiar with decision trees being related to tree-like resolution. And in the original Karchmer-Wigderson paper, they showed that communication protocols for the Karchmer-Wigderson game correspond directly to Boolean formulas. But it turns out that we can actually go further than this. Like we don't have to stop just at tree-like resolution and decision trees and communication protocols and formulas. And in fact, in recent work, we've seen sort of a much bigger things have been able to capture this way. So we can capture much more flexible circuit models. We can capture lots of different query models. And it turns out that there's sort of natural relationships between many query complexity measures and many proof complexity measures, and also many circuit complexity measures and communication complexity measures. So in recent work with Mika Gus, Pratish Kamath, and Dima Sokolov, and this is building on lots of work back in the 90s and even in the past, and in this related thread of work in bounded arithmetic, we sort of suggested to use, that should be TFNP, TFNP classes as kind of a guide to find different models to capture different circuit and proof classes. Okay, so if you want to talk about this, if you want to describe this talk in one diagram, it's basically this. So this talk is going to be sort of at the intersection of proof complexity, circuit complexity, and TFNP. So my goal for today is basically to tell you two stories. So this is supposed to be kind of tutorial in style. So first, I'd like to tell you about this false clause search problem in proof complexity, and in particular, the setting in which it originally came up. Then I'd like to talk about the Karchmer-Wigderson games and circuit complexity. And then finally, I'd like to argue that these two stories, which are like sort of grew independently of one another historically, and there were some relationships between them, but it wasn't really clarified. They're actually two pieces of this sort of bigger theory of query and communication TFNP. And in particular, I'd like to outline kind of a research program that uses TFNP as a guide to capture these proof systems and circuit classes. Okay. And of course, if you've seen the talks yesterday, there's lots of close thematic links with Sam's and Neil's talks from yesterday. So this is not this is far from the only approach to thinking about proof complexity using TFNP. There's been lots of results by Sam Buss, Neil Toppin, and their co-authors, and Jan Krajcek, who's going to be speaking later, which have already witnessed these kind of connections back in the 90s. So this is far from the only way of looking at it, but this way is somehow a more non-uniform way of looking at it in some sense. Okay, so if that's good, then I'll start off by telling the first story. So this is about proofs in this false clause search problem. And I'd like to say here, feel free to ask any questions in the chat or pause me and ask questions if I'm going too fast. So in proof complexity, we're usually focused on the complexity of refuting unsatisfiable CNF formulas. Okay, so a CNF is just a conjunction of clauses where each clause is a disjunction of Boolean literals. And associated with F is this, it turns out to be very natural total search problem. So I'm going to call it search F. And the basic idea is that for a fixed unsatisfiable formula F, when we're given an input assignment to the variables of F, we want to find some clause I that's false under that input assignment. And it's most natural to study this problem in the model of query complexity. So like querying different inputs of this X in order to find one of these false clauses. And kind of the main theme of this section is that the query complexity of this search problem turns out to be very closely related to the proof complexity of F. In fact, in some sense, they're kind of the same thing, at least for weak proof systems. So let's kind of warm up slowly. So I'll talk first about resolution proofs. So probably everyone here has seen this before. So in a resolution proof of an unsatisfiable CNF, lines are clauses, okay? And we deduce new lines from old ones using the resolution rule. And the resolution rule just says, if I have C or X and D or not X, well then, on any Boolean assignment, one of these has to be false. So that means that C or D better be true, right? So over on the right-hand side here, I have an example of a resolution proof. So the length of the proof is going to be the number of lines in the proof, or the number of nodes in this proof DAG here. And the depth is going to be, the length of the longest path, okay? And the proof is tree-like if each clause in the proof is used at most once as an input to the resolution rule. Excuse me. But of course, input clauses to the formulas, we can copy them many times if we want. So for example, here's a resolution refutation of this unsatisfiable formula here, and we can see that it's not tree-like, it's DAG-like, because this clause is used as the input to two rules. And if we wanted to turn this into a tree-like proof, well, the most obvious way to approach this is to just, recursively copy this subtree 2 times, right? Okay, cool. So not too hard. Now, sort of the query complexity analog that we'll see for these resolution proofs are decision trees for this search problem. Okay, so probably we all know what a decision tree is. The basic idea is that we query some input variables of our assignment, and then that each query tells us what the value of the variable is, and then at the leaf we want to output something. Okay, so the size of the decision tree is going to be the number of nodes. The depth will be the length of the longest path. And the idea is that, given a Boolean assignment to these variables, we'll just follow the unique path in the tree that's consistent with that, and then just output whatever's on the leaf here. So in this case, here's an unsatisfiable CNF, which basically is like the induction principle, if you like. It says that, X1 is true, and X1 implies X2, and X2 implies X3, but X3 has to be false, right? So in other words, X1 implies X3, but X3 has to be false. And a way to solve this, the unsatisfied search problem here, so unsatisfied clause search problem here, is to simply do sort of a binary search, right? Like we can query this middle variable, X2, and then if X2 is false, then we know that there's a contradiction this way. And if X2 is true, then we know that there's a contradiction this way, right? So continuing in this way, we can eventually, at each leaf, we can find some false clause to this underlying formula. And the decision tree for search F is closely related also to this DPLL method for solving SAT. So this was sort of one of the original, the obvious sort of backtracking algorithms for solving SAT, where you just query variables and recursively do things. And this is, as far as I understand, this is originally where this idea of relating decision trees to tree-like resolution sort of came from. Okay, so now I said earlier that tree-like resolution is sort of equivalent to decision trees for the search problem. So what do I mean by that? Well, from a tree-like resolution proof, I can construct a decision tree and vice versa. Like in fact, these are kind of the same object. And so what's the idea? Well, I can give you one direction. So if we have a tree-like resolution proof, what I'm going to do is I'm going to start at the top here, and I'm just going to query the variable that was resolved on at each step. Okay. So here the last variable that was resolved was X2. So I'll start by querying that. And then the idea is that I'm going to go to the side where the clause remains false, right? So if x2 is 0, I'll walk down to this node, and we can see that this assignment falsifies this clause. And if x2 was 1, well, then I would go over here and I'd see the assignment falsifies the other clause, right? So then, if we walk down to here and then I query x1, well, now just by that invariant that we just saw, we know that when I reach an input clause, it'll be falsified by the assignment on the path, right? So just sort of padding out the tree in this way, well, we end up with this picture right here. So just to sort of solidify this isomorphism here, the variable resolved corresponds to the variable that was queried, and the partial assignment at each node falsifies the corresponding clause in the line of the resolution proof. So, and this is only one direction, but the reverse direction also works. To go the other way, you'd have to do kind of you start with a decision tree, and instead of going from the top down, it's kind of most convenient to go from the bottom up. Like basically querying a node is just equivalent to resolving on a variable. So you do this, and this gives you basically this theorem. So for any unsatisfiable CNF formula, well, we have a size S depth D tree-like resolution refutation, if and only if we have a size S depth D decision tree for this search problem. And like, while I can write this down as a theorem, I think the moral is somewhat stronger than this. Like it's actually saying like these are kind of just the same object, right? Like the decision tree is kind of like the negation of a tree-like resolution proof in some sense, right? Okay, cool. So let's take a step back, and I'd like to think about decision trees actually more generally, like decision trees solving total search problems in sort of a more general realm. So here's a very general setup for solving total search problems. So if O is a finite set and S is just some relation on this cross product right here, then I'm going to let S of X for some input X be the set of O's such that X and O are in the relation. Okay, so this is the set of feasible solutions. So I'm thinking about S as being a search problem where I get an input here and I want to find an O such that this is in the relation. And this search problem is total if there's always a feasible solution for every single X. Okay, so the false clause search problem we saw a second ago is an example of a total search problem, but that's just one example, right? You could think of many other total search problems. So with this, we can define some complexity classes. So I'll define basically P, the decision tree P of S, to be the query complexity of solving S. And this is just the depth of the shallowest decision tree that solves S, okay? And then I'll abuse notation a bit, and I'll say that FP to the DT is just all the search problems with polylogarithmic decision tree depth. Okay, cool. Well, since we have a P, we also have to have an NP. So let's talk about what the NP should be in this decision tree setting. And I'm going to call it TFNP because we're solving search problems rather than just regular decision problems. So in NP, well, the idea is to have a non-deterministic algorithm which guesses some coordinates that we then want to verify. Okay. So when you set this up appropriately, you get something like this. So if S is a total search problem, then a certificate of S is a partial restriction such that basically there's some output that is consistent with every input that is consistent with this restriction. Okay. And then a certificate cover is just a set of certificates that covers all of the inputs. Okay. And then the way to think about this ultimately is as an NP algorithm. So the idea is like given some input X, we non-deterministically guess some certificate in the cover, and then we can verify that X is consistent by querying the coordinates that are fixed in this partial restriction. Okay. And then every certificate has some output which is consistent with it. So that means that once I have verified that X is consistent with the certificate, then I'm done. I can just output whatever that certificate is. Okay. So in this non-deterministic algorithm, the complexity should be like, the worst case number of queries I need to make. And that's exactly what TFNP DT is going to be defined to be. So it's just the best possible cover of the maximum number of queries that you need to make inside the cover. Okay. And once again, I'm going to abuse notation a little bit, and I'll say that the TFNP, the class, is going to be all the total search problems with polylogarithmic certificate complexity. Now, with this, you can ask what's so special about this search problem. And if you think about it, if I have an unsatisfiable CNF, the certificates are the clauses, right? Like maybe there's other ones, but a natural set of certificates are the clauses of the formula. Because if I ever just query all the variables in one of the clauses, then I can determine if that clause is false or not, right? So this tells us that the TFNP complexity of search F is at most the width of this CNF, like the width of the widest clause. But in fact, it turns out that these search Fs are very special. And this was already sort of remarked upon by Sam in yesterday's talk. And that is, search F is in some sense complete for TFNP, in that any total S, which is in TFNP, can be reduced to solving search of F. So why is that? Well, it's simple. It's just that if I have a set of certificates for S, if it's in TFNP, then I can just take the conjunction of the negations of the certificates, right? Just take all the certificates and negate them. And then like clauses are certificates, right? The certificates of this, the clauses of this formula are the certificates of this total search problem right here. So then I can solve the search problem here, which will give me a certificate for S, and then I can solve S just using that certificate, right? And then under some reasonable, assumptions, the converse also holds. Okay, so this is what I mean when I say search F is somehow complete for TFNP. Like it's like the canonical example of a TFNP problem when the width of the CNFs are small. Okay, cool. So to summarize this first part, any unsatisfiable CNF has an associated search problem. The decision trees for the search problem are just the same as tree resolution refutations of F. And in some sense, this search problem is sort of complete, or at least canonical, for examples of search problems in TFNP. And the question I'd like you to keep in mind for the future of this talk is like, can we capture other proof systems? Like, is it possible maybe to go beyond tree resolution? And we'll see the answer is actually yes. Okay, so this may be a good time to answer a quick question, if anyone has one. Otherwise, we can soldier on. Okay. So now I'm going to tell you a story about circuits in the Karchmer-Wigderson game. Okay. And this story is going to look very, very similar to the one that I just told. So what's the Karchmer-Wigderson game? Well, now we're going to switch gears, and we're in the realm of circuit complexity. So we're interested in the size of the smallest circuit that computes a Boolean function. Okay. So given a Boolean function f, I'll say that f is monotone if whenever x is less than y, coordinate-wise, then f of x is less than f of y. So think like clique, something like that. If I keep adding edges, then I can't make a clique disappear. And f is going to be a partial function if, I don't care what the output is on some of the inputs. Okay. And now Karchmer-Wigderson showed in the 90s that, well, any Boolean function f has an associated total search problem, which somehow captures the complexity of f in the same way that the clause search problem captures the proof complexity of unsatisfiable CNFs. So, and the Karchmer-Wigderson game is defined as follows. So it's a two-person game now. So given x, which is a 1 of f, and y, which is a 0 of f, we want to find some coordinate such that xi is different from yi. Okay. And the moral of this game is that somehow the circuit complexity of f is the same as the communication complexity of the Karchmer-Wigderson game of f. And in fact, if f is a monotone function, then we can actually restrict the game a little bit, make it a little bit harder. And this is the monotone Karchmer-Wigderson game. And now instead of just asking for a coordinate where xi is different from yi, we want to find a coordinate where xi is strictly bigger than yi. So in other words, where xi is 1 and where yi is 0. Okay. And such a coordinate must always exist, because if it didn't, then x would be less than y, but then f of y would be 1, which is a contradiction, right? And this game will turn out to be very important for us. The monotone game turns out to be very important, as we'll see. So here's a quick primer on Boolean circuits. Again, probably most people are familiar with this. So a Boolean circuit is just a device to compute a Boolean function. Starting from some Boolean literals, we use and OR gates to compute some target function. The size is the number of gates. The depth is the length of the longest path. And just like in proof complexity, the analog of a tree-like circuit is a formula, which is just that if any gate ever gets reused, is never reused, then it's a formula. So over here, we have a Boolean circuit that's computing some function. I don't know, I just drew something random. And we can see that it's a DAG here because this gate is being used twice. And so if we wanted to make it a formula, we would just, again, duplicate this subcircuit. Okay. So corresponding to Boolean circuits, we have communication protocols for the Karchmer-Wigderson game. Okay. So now we're in the setting of deterministic communication complexity. And now, so we have two players, Alice and Bob, and they can communicate over some communication channel. And the idea is that Alice is going to get one input to the Karchmer-Wigderson game. Bob will get the other input to the Karchmer-Wigderson game. And they want to communicate bits back and forth across this channel and then so that they can agree on a solution to the game. Okay. So in the standard Karchmer-Wigderson game, the goal is to communicate and then find an I such that xi is 1 and yi is 0. Okay. And this is usually formalized in terms of a protocol, which is just like a tree that Alice and Bob agree on beforehand that just tells them who speaks at every single point, right? So this should look very similar to a decision tree, right? This is the analog of a decision tree in this circuit complexity setting. And then once again, so the depth of the tree is the length of the longest path, and the size is the number of nodes. Now, in communication complexity, one of the sort of central roles is played by these combinatorial rectangles. So if I have a set U cross V, then a rectangle in U cross V is just a cross product in U cross V is how I think of it. So you take some subset of U and some subset of V and then take a cross product. So it looks like some rectangle here. And the reason that these are important in communication complexity is because since only one player speaks at any given node, all of the assignments that reach any given node in a protocol forms a combinatorial rectangle, right? Every player can only ask a question, can only send a bit based on their input. So this ends up partitioning the input space up into combinatorial rectangles. So just like tree resolution was very similar to decision trees, it turns out that Boolean circuits, or in particular Boolean formulas, correspond very directly to communication protocols for this Karchmer-Wigderson game. And the proof is basically the same as the proof that I showed you in the previous section. So how do Alice and Bob use a Boolean formula to solve this game? Well, Alice has some input to her function, some private input. That's a 1 that makes this formula output 1. And then Bob has an input that makes them output 0. And then so we evaluate every single gate, on their inputs. And then they start at the top and then they just start communicating. So if we're at an OR gate, then Alice will speak because she has a 1. And so she can tell us where the next 1 is that they should step to. So in this case, she sees it's here, so she'll step down to this gate. When we're at an AND gate, Bob speaks because he has a 0 of the thing. And so he can tell us where to go to find a 0 of the thing. So eventually, by walking down in this way, they'll end up at a leaf of the formula where their inputs, where it's actually a different input bit, right? And so you pad this out, and then roughly the correspondence here is that Alice corresponds to OR gates and Bob corresponds to AND gates. Okay. And once again, just like in the decision tree setting, the reverse direction also works. So proceeding from the bottom up, you can actually use this to construct a formula from a communication protocol that solves this game. Okay. So Karchmer and Wigderson, sorry, I'm missing a citation here. This is Karchmer and Wigderson. Karchmer and Wigderson showed in the 90s, they proved this result, and they showed I have a size S depth D Boolean formula for F if and only if I have a size S depth D communication protocol. And once again, the correspondence is somehow stronger. Like these are essentially the same object in some sense. And they also showed a stronger statement for monotone Boolean functions. So if I start with a monotone function, then I get a monotone Boolean formula. So that's something without NOT gates. If and only if I have a protocol for the monotone Karchmer-Wigderson game. Okay. And in fact, we just saw that on the previous slide because the game terminated at a leaf where Alice was guaranteed to have a 1 and Bob was guaranteed to have a 0. Okay. Cool. So let's take a step back and generalize a little bit. Let's talk about total search problems in communication. So we can do a very similar setup to what we just saw. So if x, y, and o are finite sets, then I can take a search problem in x cross y times o. Now this is kind of the input. X cross y is the input of the problem. And o is the output. And we'll say, once again, that we have a set of feasible solutions. This is just the same setup. And we'll say that S is total if every input has some feasible solution. Okay. And now communication P of S is going to be the communication complexity of solving S, or in other words, the depth of the shallowest protocol that solves a total search problem. Okay. And once again, we'll abuse notation and we'll just call P as the set of all search problems that have polylogarithmic communication complexity. And then once again, we can have, just as we had a P, we also need an NP. So there's also a communication NP for search problems. And now, well, I called it a certificate cover here, but I mean, really, you could call it it's probably better known as a rectangle cover. So now Alice and Bob will non-deterministically guess some rectangle that's consistent with an output. And then they want to find and then they can just communicate one bit back and forth to verify that they're inside of that rectangle. So once again, we have a natural NP algorithm where given X and Y, they just non-deterministically guess some rectangle in here, and then they verify that X, Y is in R by exchanging one bit of communication. Okay. And now I can explain what I remarked on earlier when I said this monotone game is very special. So it turns out that the monotone Karchmer-Wigderson game for partial functions plays the role of the unsatisfied clause search problem. So it's complete for TFNP in some sense. So if I start with a partial monotone F, then there's a natural rectangle I can associate with every input, which is just like, for all the ones, I take the places where xi is 1, and for all the zeros, I take all the places where yi is 0. So if I take all of these rectangles, then this is a rectangle cover because we know that all of the solutions are equivalent to this. And therefore, the NP complexity of the Karchmer-Wigderson game is no more than log n. They can just guess one of these inputs and then verify that that coordinate is different. Now, what's kind of amazing is that a sort of completeness result also holds here. So every rectangle cover of a set U cross V is equivalent to this monotone Karchmer-Wigderson game for some partial monotone Boolean function. And this was essentially observed by Razbarov in 1990, but it was really formally pinned down by Anna Gal in 2001. So let's see what this looks like. Well, if over here I have some search problem with some rectangle cover of it, then how do I create a Boolean function such that the monotone Karchmer-Wigderson game corresponds to this search problem? Well, for every input U, I'll just write down the list of rectangles that U lies in. So that in this case, it will be 1, 1, 0, 0, right? Because this U hits rectangle 1, rectangle 2, but it misses 3 and 4. And similarly, for each V, I'll write down now not the set of rectangles it hits, but the set of rectangles it misses. So yi will be 0 if and only if vi is in R1. So this V will be 0 for R1, 0 for R3, 0 for R4, and 1 for R2. And you can see where they intersect R1 right here. This is the coordinate on which they are different. So I'll just define my function in this way. I will define f to be 1 on all of these x's, and I'll it'll be 0 on all these y's. And you can prove that this is actually a partial monotone function. Okay, so the monotone Karchmer-Wigderson game of this defined function just captures what this MKW just captures this search problem completely. And so the lesson is that any total search problem S is just more or less equivalent to the monotone Karchmer-Wigderson game for some partial f. Okay. So once again, the summary is very similar. Like any Boolean function has a Karchmer-Wigderson game. Communication protocols correspond to Boolean formulas. And also this monotone Karchmer-Wigderson game is in some sense complete for TFNP. Okay. And you've probably observed that the two stories that I've told you are just the same story where I've switched out some of the actors, right? In both cases, bottom-up models, like proofs in one hand and circuits in the other hand, are kind of captured by top-down algorithms, right? Decision trees and communication protocols. And the main actors that get switched are the search problem in the proof setting versus the Karchmer-Wigderson game in the complexity setting. So these two search problems kind of capture the complexity of these processes. They're canonical examples of the TFNP classes. And now we're going to try and generalize a little bit and tell you a little bit about a general theory that captures both of these things.
Can I ask a quick question, Robert?
Yeah.
So you said these stories are the same, but I mean, they seem a bit different in that monotonicity seems to play a special role for the communication complexity setting, but not for the query setting. Could you just say a bit about that?
That's true. The reason why the reason is that the monotone Karchmer-Wigderson game, even though it looks more restrictive, it's actually less restrictive. That's kind of the lesson here. In fact, that's why it's hard, right? Like if it was easier than the regular Karchmer-Wigderson game, then we would have non-monotone circuit lower bounds. So the monotonicity plays a special role because solving the Karchmer-Wigderson game is actually harder, not easier. And it's actually can be so much harder, it can capture any total search problem at all. That's kind of the lesson of it, I think. Okay, cool. So in my last couple minutes, I'll try and sketch this sort of general TFNP program. So this classical theory of TFNP we saw yesterday in Neil's, we saw yesterday a little bit in Neil and Sam's talk. It basically is in the classical complexity setting where everything is in the realm of Turing machines. So this is the class of NP problems where a witness always exists. Subclasses are then defined by some reductions to particular problems. And these problems are usually representing theorems that prove existence results. So for example, the handshaking lemma, these fixed point theorems, Sperner's lemma, and there's tons of connections of this theory with other fields, okay? So let's give a quick example. So the handshaking lemma. So every graph has an even number of odd degree nodes. Well, the way to turn this into a search problem is as follows. It's this PPA problem. And the idea is we have a set of nodes V, some distinguished node, and a neighborhood function with every node here, with basically all the neighborhoods have to be size at most 2. Okay. And now the feasible solutions of this thing, well, what I'm going to do is I'm going to evaluate this neighborhood function on all the nodes to create a graph. And then the solutions will be this distinguished node if the degree is not 1, or any other node if the degree is 1, right? So in other words, right here. So these are all degree 1 nodes. And so basically I'm forcing one odd degree node into the graph. And so the solutions are any other odd degree node. Okay. And in the classical theory, you create a complexity class by basically doing like Turing reductions to this problem. Okay. So you have some Turing machines which take an input and then output an instance of this problem and then line everything up so that the solutions here correspond to the solutions to the problem you're trying to solve. Okay. So there's a big family of subclasses of TFNP. I mean, this is far from the only one. And here I've kind of labeled some of these canonical classes. And these were all classes that were introduced in Papadimitriou's original paper. Of course, we saw earlier lots of other classes. And I've labeled here the classes with like the principles that kind of capture them. So we just saw that PPA kind of corresponds to this handshaking lemma. We also have classes that correspond to various forms of the pigeonhole principle, like PPAD, PPADS, and PPP, and also this like local minima principle that every DAG has a sink. Okay. And now we also just saw communication and query versions of P and NP. right? So it's very natural to kind of bootstrap off of this TFNP stuff and define these other classes by reductions, okay? And in order to do this, we'll use, rather than using Turing machines, of course, we'll use shallow decision trees or shallow communication protocols. So maybe I'll just skip past my example here because I'm running a little bit low on time. But I can say, so if we look at the query version of PPA, which is defined by decision tree reductions to this handshaking lemma, then in one direction, Beam et al. Observed in the 90s that basically if I have a PPA reduction, then I get a low degree null-Stellensatz proof. And we recently observed the converse, like in fact, actually low degree null-Stellensatz over F2 gives a reduction to PPA. So in fact, PPA decision trees are kind of exactly the same as low degree null-Stellensatz over F2. So here's some of the proof systems which have been characterized sort of in terms of these TFNP classes. So we saw in Sam and Neil's talk that resolution captures PLS and null-Stellensatz captures PPA. Well, in fact, it turns out that we can actually assemble a bit of a zoo here. So in kind of recent upcoming work, for a lot of these other classes, we've been able to capture them in terms of proof systems. So some of the prominent examples here are like PPADS turns out to correspond to low coefficient Shirley atoms. And more interestingly, the most interesting result here, I think, is that we're able to characterize the intersection class PLS intersect PPADS in terms of a problem called sink of potential line. And we can even give a proof system which corresponds to this, which is a sort of reversible form of resolution. And so this leads us to a kind of a nice result, which says there is a size S with W reversible resolution proof if and only if there is an efficient resolution proof and an efficient low coefficient Shirley atoms proof. And this is very neat. I've never seen a result like this before. This is characterizing a complexity class in terms of the intersection of two other complexity classes. And now we can also do a similar sort of setup for TFNP. And this is what we did in this original GKRS paper, this adventures paper. We showed, yeah, okay. In fact, PPA corresponds now with communication reductions to the class of span programs. And then classic results correspond to Boolean circuits. And then the original Karchmer-Wigderson sort of corresponds to FP, corresponds to Boolean formulas. And these other results haven't been formally filled out yet, but we have conjectures for what they should all be. So PPAD should be efficient span programs. PPADS should be extended formulations, and sink of potential line, I think, should correspond to some kind of bounded fan-out circuits, like comparator circuits or scatter-free circuits. Okay. So I'm running a little bit. Yeah.
I feel like I should say that it's 12:45.
Yeah, I'm going to stop now. Yeah. So I'm running out of time here, so I'm going to skip ahead to kind of my last slide. So the basic idea here is to sort of relate query TFNP to communication TFNP. So now to bring it back to the beginning of the talk where we have these systematic relationships between query complexity and communication complexity, well, this gives a method of characterizing these various classes using query models and communication models. So in one direction, we have these sort of classic feasible interpolation results, which give us a connection one way, and lifting theorems give us a connection in the other way. So the thing that I'd like to kind of advocate for is to search for more results of this kind, and sort of seek out other examples of TFNP classes that capture these things. So yeah, so thanks for listening, and yeah, I should probably quit so that Jan can get to his talk. Thanks.
Thanks a lot, Robert. It's a great talk. So yeah, so perhaps we can leave questions for the end or for GatherTown. And Jan, I don't know if you would like to share your slides.
Share screen.
Yes. So this next